Okay, in today's lesson, we're going to look at a couple of things. Firstly, we're going to look at the intersection of a line and a plane. And then I'm going to make a second video, and that's going to look at the intersection of, it's going to look at the distance from a point to a plane, the shortest distance from a point to a plane. So there's two parts to today's lesson, and I'm going to make two videos for that. So to start off, we're looking at the intersection of a line and a plane. So let's start by constructing a plane, and through this plane we've got a line that extends like so, and we're looking to find this point here. Let me perhaps highlight that in a different color. So this is my point of intersection that I'm after. Let's call that P. And I have a plane, and my plane has equation, let's say 3x minus 2y plus 5z is equal to 15. So defined by that, every point on this plane has to obey that rule, 3x minus 2y plus 5z equals 15, and we can test points to see whether it lies on the plane or not. We want the intersection of the plane and the line. Now I'm going to define the line here by in base vector format. So it'll be, say, 1 minus 2t I plus 3 plus 4t j. So t is my parameter. Sometimes we see lambda in there, just mixing it up a bit, plus tk. So that's the equation of the line. So what we get from this, and what we're going to need to do in order to find this common point, is I'm going to need to extract from my line equation what my x, y, and z points are in terms of t, and then sub them into my plane equation. So solve simultaneously, essentially. So from this we can say that, that x is equal to 1 minus 2t, that y is equal to 3 plus 4t, and that z itself is just equal to t. So what we're going to do now is, so this defines for different values of t. So if I put t equals 1 in here, then I would get x is equal to -1. I'd get y is equal to 3 plus 4 is 7. I'd get z is equal to 1. So -1, -1, 7, 1 will be a point on the plane. So that's a point on the line. It's not on the plane. What I'm trying to do is find the x, y, z point that is common to the one on the plane as well. So -1, 7, 1. We could test to see if it sits on the plane. It would be a massive fluke if it did, because that was just a random value of t. Remember, t has an infinite number of values that we can substitute in, get our infinite number of points for x, y, z that constitute our blue line here. That's defined in this way. So if I put -1, 7, 1 back up here, then we could test it. We could test it into this equation, and we would get 3 times -1 minus 2 times 7 plus 5 times 1, and that's equal to -3 minus 14 plus 5, so minus 17 plus 5 is minus 12. So no, it does not sit on this plane. It sits somewhere. It sits on the blue line, but it doesn't sit on the plane. We want the point that also sits on the plane. So we're going to, I'll just remove all these workings now. We're going to substitute our value, our x, y, and z, our x, y, z point. So we're going to go in and we're going to substitute our point 1 minus 2t, 3 plus 4t, and t. We're going to substitute that into our equation of the plane and make it equal 15. and then we'll find the value of t that solves it. So let's do that, and I'll drop down below in order to do that. So that's going to be substitute into equation of plane. Equation of plane. All right, now we'll do that, but we'll drop down here to do it. So we'll get 3 by 1 minus 2t minus 2 by 3 plus 4t plus 5 by t, and that we are going to make equal to 15 in order for this to also satisfy the equation of the plane. So therefore 3 minus 6t minus 6 minus 8t plus 5t is equal to 15, and therefore we've got minus 14 plus 5, we've got minus 9t, we've got 3 minus 6 negative 3, we've got plus, so it's 18, so therefore t is equal to negative 2. When t equals negative 2, we have a point that sits on the plane, so therefore at t equals negative 2, so we can say therefore my point of intersection is 1 minus 2t, so 1 minus twice negative 2, so that would be 5. 3 plus 4t, 4 times negative 2 is negative 8, so 3 plus negative 8 is negative 5. And negative 2. 5, negative 5, negative 2. Now we could go and we could test. So we could test. And so that point substituted into, we know that at t equals negative 2, so we know it's on the line, but now we just test it on the point, so, on the plane. 3 times 5 minus twice negative 5 plus 5 times negative 2. That's equal to 15 plus 10 minus 10, which equals 15, which equals right hand side. So therefore P lies on the plane. Lies on the plane pi. P lies on plane pi, as defined by pi. Okay, let's do another example. Okay, here's the example. We have a line with defined by this vector equation and the plane defined by this Cartesian equation. They intersect at a point P, find P. Okay, so let's go to work on this. Our process is to find from the equation of the line, we need to find x, y, and z in terms of its parameter. In this case, the parameter is lambda. So therefore, so we've got r equals okay, so we want to group our x, y, and z. So r will equal 2, just reorganizing what we see here. It'll be 2 plus lambda I. Now in terms of j, what have I got? I've got minus 1 minus lambda, so it'd be plus minus 1 minus lambda j. And then in terms of k, we've got 3k plus 2 lambda k. So it'd be plus 3 plus 2 lambda k. So we can pull from that. We can pull from that x is equal to 2 plus lambda, y is equal to negative 1 minus lambda, and z is equal to 3 plus 2 lambda. Now we can pop those values into the Cartesian equation, so we get twice 2 plus lambda minus 1 minus lambda plus 3 plus 2 lambda plus 2 is equal to 0. Now we just solve this for lambda and then substitute back in to find our point of intersection. So we get that lambda is equal to negative 2, And so therefore, my point of intersection is 2 plus negative 2, so 0 for x. Y is negative 1 minus negative 2, so negative 1 plus 2. And z is 3 plus twice negative 2, which is negative 1. So my point of intersection, 0, 1, negative 1. Okay, I think we need to get some practice. So exercise 11p on page 606. And the first two questions I think would be good for you to do. And then I've got another video for the next part of today's work.